In the last video, we answered the question that if a ball was dropped from a 10-meter building, how long would it take to hit the ground? But what if instead of dropping the ball, we threw the ball up into the air instead? How long would it take to hit the ground then? Well, the good news is we don't need any new equations. We already know everything that we need. In this lesson, I'll show you how to solve free fall problems like this one using the same four kinematic equations from the last video. So going back to our initial problem, I'm first going to resolve the ball just dropped from 10 meters. If you already caught this in the last video, you can go ahead and skip to the appropriate timestamp. But if you drop a ball from a 10-meter building, let's write first what we know. We know that the change in y is equal to 10 meters. We know that the acceleration due to gravity, we're going to say that it is negative 9.8 meters per second squared. So we'll choose up to be the positive direction. And then we know the initial velocity, since it is dropped, not thrown, equals 0. And we want to know how long it takes to reach the ground. So we want to know time. The thing that we're missing is we have no final velocity. The equation without final velocity in it is change in y, so our displacement is equal to initial velocity times time plus 1/2 a t squared. This term cancels out because initial velocity is equal to 0, and we're left with just delta y equals 1/2 a t squared. We can rearrange this to solve for t, and you find that t is equal to the square root of 2 times the change in y divided by acceleration. So this is the square root of 2 times 10 divided by negative 9.8 meters per second squared. Now there's a slight problem with this equation. We said that up was the positive direction. And you'll notice here that we have 2 times 10, which is 20, divided by a negative number. So we have the square root of a negative number. Since we chose up to be the positive direction, our displacement from the start is actually negative 10 meters. So then this value is negative, both of them are negative, and we end up with a positive value. And that number is, so delta y is roughly equal to 1.43 seconds after you plug it into the calculator. It's really important that if you choose your coordinate system, you stick with it for all of your values, your displacement, your acceleration, whatever it may be. For the sake of more practice with kinematic equations, let's say that instead of wanting to find time, we wanted to know the final velocity, or the impact speed right before it hits the ground. So now we know delta y, acceleration, initial velocity, and we want to know the final velocity. There is no time. So the kinematic equation without time is final velocity squared equals initial velocity squared plus 2a delta y. This is already set up properly because we have initial velocity, acceleration, change in displacement, change in position. So we can just plug in our values, and we get that final velocity is the square root of, well, initial velocity here is 0, so this term cancels. We have 2 times negative 9.8 times 10. And the square root of that is going to be roughly equal to 14 meters per second. So that's the impact speed right before it hits the ground. Notice that we solved two completely different questions using two different equations, but we're given the same starting information. Let's revisit this problem one more time, but now let's give it some initial velocity. Let's say we throw it upwards at an initial velocity of 10 meters per second. So we'll put that here. And that's positive because we're throwing it upwards. We still use the same equation from earlier, which is delta y equals initial velocity times time plus 1/2 a t squared. Let's plug in our values. We've got negative 10 equals 10 times time plus 1/2 negative 9.8 t squared. I'm going to simplify this to 4.9, which is just 9.8 divided by 2. So minus 4.9, and then t squared. Now, if we rearrange this equation, it may look a little more familiar. I'm going to add 4.9 t squared and subtract 10t from both sides. So we end up with 4.9 t squared minus 10t, and then minus 10, so this is the left-hand side of the equation. And since I took everything away from the right-hand side, it's 0. This is in the form of a quadratic equation, and so we can use the quadratic formula to solve it. Quadratic formula is going to be t is equal to negative b plus or minus the square root b squared minus 4ac all over 2 times a. In this case, a is 4.9, b is negative 10, and c is also negative 10. So here on the right, I've fully set up the quadratic formula. And then on the left are the two solutions that we get from the positive or negative in the quadratic formula. And you'll notice that one of our solutions is a negative value. There's no way to have negative time, and so we know that the correct solution is 2.78 seconds. I'll write that here. And a reminder that the only thing that we did differently here is that we had an initial velocity, which means that this value here did not cancel out anymore, and so we had to use the quadratic formula to solve for it. Before I end this video, I want to use this diagram in the bottom left to summarize what happens throughout the ball's motion. I have 3 different points here, 1, 2, and 3, that correspond to these timestamps. Here at the start, the ball is moving upwards, so its velocity is a positive 10 meters per second. But even though it's moving up, the gravity is pulling downward with the negative acceleration. Here at point 2, there's a brief moment where it turns around and the velocity is 0 meters per second. But even though it's turning around, the acceleration is still negative at 9.8 meters per second squared. Gravity never turns off, it's always acting on the ball. You could say that this moment where velocity becomes 0 is where gravity finally overcomes the ball's initial velocity and causes it to turn around. And then after the ball reaches the top, it begins falling back down toward the ground. Now both velocity and acceleration point downward, so the ball speeds up as it falls. And we didn't actually calculate the impact speed for the case with initial velocity, so I just said that the velocity becomes negative, which is the key thing to remember. Whether the ball is moving up or down, we solve every part of the motion using the same kinematic equation. The only thing we have to remember is that gravity is always going to point downwards, so we need to keep our sign convention consistent. The key takeaways for this video for solving free fall motion problems are: first, you choose a positive direction. Generally with free fall motion, up is positive, but you could choose down if it's more convenient for the specific problem. Second, you list all of the variables you have, and you give them the appropriate signs to match the direction that you already chose. Finally, you choose your kinematic equation, you plug in your variables, and you solve. In the next lesson, we'll combine everything we've learned so far to solve projectile motion problems by breaking motion into both horizontal and vertical components. And if you found this lesson helpful, please consider subscribing. I'm building a complete Physics 1 course here on YouTube with new lessons every week. Thanks for watching, and I'll see you in the next one.